In this guide, why AI agents need cryptographically verifiable identity, not just an API key. How verifiable credentials and DIDs create a trust triangle for agent attestation. What the issuance, presentation, and verification payloads look like on the wire. The threat model when agents carry credentials autonomously. And where the EU AI Act and NIST AI RMF are pushing agent transparency next. Identity Expert, powering you to be an expert in identity. Imagine this: your company deploys an AI procurement agent. It negotiates with suppliers, places purchase orders, and commits budget all autonomously. One morning, a supplier fulfills a large order your agent never placed. A rogue agent running on infrastructure you do not control impersonated your legitimate agent. It used the same API endpoint, the same message format, and a plausible-looking bearer token. The supplier had no way to distinguish the fake from the real one. This is not a hypothetical. As AI agents proliferate across enterprises, supply chains, and financial systems, the question is no longer can the agent authenticate. It is can the receiving party verify that this specific agent instance is legitimate, authorized by a known principal, and operating within its approved scope. Know Your Agent (KYA) is the emerging answer. It applies the same verifiable credential architecture that proves your university degree or your driving license to a new subject, an AI agent. An issuer attests the agent's identity, its capabilities, its owning principle, and its authorization boundary. The agent carries that VC. The verifier checks it cryptographically, with no live callback to the issuer. Agent identity becomes provable, not assumed. Think about hiring a contractor to work inside your home. You would not let a stranger walk in and start rewiring your kitchen just because they said they were an electrician. You would ask for a license issued by a recognized authority, proof of insurance from a bonding company, and a work order from the homeowner who authorized the job. The license is a verifiable credential, signed by the issuing authority, tamper-evident, and verifiable without calling the authority. The proof of insurance is a second VC from a different issuer, providing independent attestation of the contractor's standing. The work order is the delegation chain, evidence that the homeowner authorized this specific contractor for this specific scope of work. Now replace the contractor with an AI agent, the house with your enterprise API, and the homeowner with the human or workload that deployed the agent. KYA gives the receiving system the same three-check verification: who issued the agent's identity, what authority backs its claims, and who authorized it to act. Today's agent identity has four structural gaps. First, bearer tokens prove nothing about the agent itself. An OAuth access token says this token was issued to a client. It does not say this client is a genuine, unmodified instance of the software it claims to be. Any agent that obtains or intercepts the token can use it. Second, there is no standard agent attestation format. Platform-specific signals like Android Key Attestation or Apple App Attest exist for mobile apps, but there is no equivalent for server-side AI agents, container workloads, or multi-model orchestrators. Every receiving system builds bespoke verification or skips it entirely. Third, delegation context is invisible. When an agent acts on behalf of a user, the receiving party typically sees only the access token scopes. It cannot verify the full chain, which human authorized which agent through which intermediary with what constraints. Fourth, revocation is an afterthought. If an agent is compromised, there is no standardized mechanism to propagate that revocation to every party the agent has interacted with. Cached tokens, stored credentials, and downstream delegated grants survive long after the agent should have been disabled. KYA addresses all four by giving agents a cryptographically verifiable identity document that travels with every request. KYA uses the W3C Verifiable Credentials Trust Triangle Issuer-Holder Verifier, adapted for autonomous software agents. Step 1. Agent registration and DID creation. The agent operator registers the agent with an identity authority, an enterprise identity provider, a trust registry, or a domain-bound issuer. The agent receives a decentralized identifier, a DID, which resolves to a DID document containing the agent's public key. Step 2. Credential issuance. The issuer creates a verifiable credential asserting the agent's identity, its owning principle, its authorized capabilities, and its operational constraints. The VC is signed with the issuer's private key and delivered to the agent. For lightweight deployments, the credential uses SD-JWT VC format, allowing the agent to selectively disclose only the claims the verifier needs. Step 3. Presentation at the point of interaction. When the agent calls an API, submits a transaction, or communicates with another agent, it presents the VC inside a verifiable presentation, signed with the agent's own private key. This proves the agent possesses the credential right now, not just that the credential exists. Step 4. Cryptographic verification. The receiving party resolves the issuer's DID to obtain the issuer's public key, verifies the credential signature, then verifies the presentation signature against the agent's DID. No callback to the issuer is required. The verifier knows the credential is authentic, unmodified, and held by the agent presenting it. 3 payload formats matter for agent KYA. First, the W3C VC Data Model 2 JSONLD credential. The @context array declares the W3C credentials vocabulary. The type array includes verifiable credential and agent attestation. The issuer field is a DID. The credential subject block carries the agent's DID, the owning principal, authorized capabilities as an array of scope strings, and an operational boundary describing the approved runtime environment. The proof block holds the issuer signature. Second, the SD-JWT VC format. This is the compact, selective disclosure variant preferred for bandwidth-constrained or privacy-sensitive deployments. The agent credential is encoded as a signed JWT with _SD claims for selectively disclosable fields. The agent can reveal its identity and capability scope to one verifier while withholding the owning principal from another. Third, DID resolution. Both the agent's DID and the issuer's DID resolve to DID documents. Each document contains a verification method with the entity's public key as a JSON web key. The verifier resolves both documents. The issuer's key verifies the credential signature, the agent's key verifies the presentation signature. Together, these 3 structures give the verifier everything it needs: who issued the credential, what it claims, and proof the presenting agent holds it. Agent-held VCS create a distinct threat surface because the holder is autonomous software, not a human with a wallet. Threat 1, credential exfiltration. An attacker compromises the agent's runtime and extracts the private key, then presents the agent's VC from a different environment. Mitigation, hardware-bound keys. Bind the agent's private key to a trusted platform module, a hardware security module, or a cloud key management service so the key never exists in extractable form. The VC becomes useless without the bound hardware. Threat 2, scope inflation. A legitimate agent receives a VC with narrow capabilities but attempts to use it beyond its authorized scope, relying on verifiers that check the signature but ignore the capability claims. Mitigation, mandatory scope enforcement. Verifiers must parse and enforce the capability and operational boundary claims inside the VC, not just validate the cryptographic signature. Threat 3, stale credentials after compromise. The agent's VC remains valid after the agent is decommissioned or its owning principal revokes authorization. Mitigation, short-lived credentials plus status lists. Issue agent VCS with aggressive expiry hours, not days, and publish a status list credential that verifiers check in real time. Combine with revocation event push so relying parties learn about compromise within seconds. Threat 4, impersonation via DID takeover. An attacker gains control of the domain or registry entry backing the agent's DID and publishes a new key pair. Mitigation, DID method hardening. Use ledger-anchored or multi-authority DID methods for high-value agents, and monitor DID document changes with integrity alerting. 3 regulatory and standards forces are converging on agent identity verification. First, the EU AI Act. Article 52 requires that AI systems interacting with humans or other systems disclose that they are AI. For autonomous agents operating in regulated markets, carrying a verifiable, machine-readable identity credential is the most practical way to satisfy that transparency obligation at protocol level, not just in a terms of service page. Second, NIST AI 601, the Artificial Intelligence Risk Management Framework Companion for Generative AI. It calls out provenance, accountability, and traceability as core governance functions. A VC that travels with the agent and records its issuer, principal, and capability boundary directly implements the provenance and accountability controls NIST describes. Third, the convergence of OAuth Client Attestation and W3C Verifiable Credentials. The OAuth attestation draft already defines a signed JWT, proving that a client instance is genuine software. Extending that model so the attestation is a full W3C VC, resolvable via DIDs, verifiable offline, and carrying rich capability claims is the logical next step. Early implementations are already mapping OAuth Client Attestation JWTs into VC envelopes. The trajectory is clear. Agent identity is moving from trust on first use to cryptographic proof on every interaction. KYA is the framework that makes that shift practical. All primary sources cited in today's guide are listed on screen. You will find direct links to the W3C VC Data Model 2, DID Core, the SD-JWT VC specification, the OAuth Client Attestation Draft, EU AI Act Article 52, and NIST AI 601 in the video description below. If this breakdown helped you understand the topic, please subscribe to Identity Expert. Thanks for watching. If there is another identity standard, agent security pattern, or trust framework you want covered next, leave it in the comments and subscribe to Identity Expert.